In this video, we are going to learn about complex numbers. Now, as we start to solve more and more quadratic equations, we're going to come across something called a complex number. We've already started encountering this when we've seen discriminants that were less than zero and we got no real solutions. Well, that's because those solutions are now complex solutions. Now, a complex number is based on a number whose square is -1, which initially doesn't make any sense because if you square a number, it should make it positive. But now, if we square a number, it makes it negative. Those numbers are imaginary. So we use the imaginary unit I to represent those numbers. So if you were to square I, you would get -1, and I represents the square roots of -1. So let's see how we can simplify numbers that involve I. I'll start with this square root of -7, which initially there's no perfect squares that go into 7, but I can write this as the square root of -1 times 7. And by simply looking at the square root of -1, that cannot be represented by I, which means that this number that I started with is an imaginary number, and it's labeled by this I imaginary unit because there is no number that if I square it would give me -7 unless it's imaginary. So sometimes you'll see the square root of -25. Now I know 5 squared gives me 25, but it would never give me -25, not even -5 squared, because that would be still positive 25. Again, I can start with that same step, -1 times the square root of 25. That -1, square root of -1 is imaginary. And then the square root of 25 is 5. So we get 5i. So the number you would square to get -25 is 5i, or -5i. Now let's look at the square root of -18. Again, when you see that negative underneath a radical, that's going to be an imaginary unit that you're going to multiply by your radical. So we'll get I square roots of 18. Now 18 does have a perfect square in it, so I can write this as I times the square root of 9 times 2. And the square root of 9 is 3. Now where you place it out here is actually before the I. So you get 3i square roots of 2 when you write that out front. Now, let's say we have two terms. We see here one has a positive number under the radical, and one does not have a positive number under the radical. So the number on the left, the square root of 64, we know as 8 is what we call a real number, but the square root of -12 is what we'll get called an imaginary number, because that is a negative underneath the radical. So -1 times 12 would give me 8 minus I square roots of 12. But these numbers would never combine into 1. And the square root of 12 does have a perfect square in it of 4. So I can simplify this to 8 minus 2i square roots of 3. Now when I start incorporating a real number with the imaginary number together, this makes a complex number. And all of these are complex numbers, including just real numbers too. So a complex number has the form a plus bi. So in this case, 8 would be a, and then -2 square roots of 3 would be the b part. So all numbers that we know and now can imagine would be a complex number. So if b was 0, that would give us real numbers, which is what we've been dealing with thus far. But if b was not 0, then that brings us into imaginary numbers now. Those are now included in this big set of complex numbers. And then now if a was 0 and you just had a b part, that's a pure imaginary number. I mean, there's no real part to it. So imaginary numbers have a real and an imaginary part, but if there's no real part, we call that a pure imaginary number. Now, there is the way to find an absolute value of a complex number, and I'll get back to this formula in just a minute. But first, let me show you where you can locate these numbers. So if this green axis, we call it the real axis, that represents your normal number line. But now we have a perpendicular axis we call the imaginary axis. So for this number here, -3 plus 3i, -5 is the real part, which I would go over -5, but I wouldn't graph the points. at negative 5, because that would just be my real parts. So I would go over to negative 5, and I would stop. And now I would go up or down whatever the imaginary part is, and I see here that my imaginary part is 3i. So I would go over to negative 5, and then up to 3i. And that would be where the point negative 5 plus 3i is. Now, this brings us to absolute value, which is typically the distance from 0, which on your number line, that would be right here at the origin. So what I'm trying to figure out is what is the distance from my point to the origin. That is what absolute value is. So if I'm trying to find this distance, I could use a right triangle, labeling this side here as 3, this side over here as 5, or negative 5 if you want to include that. And I could use Pythagorean Theorem to find this hypotenuse, which is the length from the point to the origin, which would represent that absolute value. So the formula I'm going to use is the square root of a squared plus b squared, which is essentially taking the Pythagorean theorem and solving for c. So if I use this formula, I can get the absolute value of negative 5 plus 3i is equal to the square root of negative 5 squared, or you could have put 5 squared, plus 3 squared. And you see I don't put the I on that. That's just because I'm using the physical distance I'm seeing here on my grid. So I don't need the I when I'm doing absolute value. Which gives me the square root of 25 plus 9, which would be the square root of 34, which is 17 times 2, so there's no perfect square there. So that would be the absolute value of negative 5 plus 3i. So the absolute value, or we like to sometimes call it a modulus of a complex number, is a real number. So because it's that distance from the origin. Now let's look at another example. Let's say it's just 2i. So 2i would be 0 for the real part, because I can see here that would be 0 plus 2i. So the real part of this number is 0, and the imaginary part is 2i. So when I go to graph it, I just go to 2i, and just looking at that, I can see what that distance is from the origin. That is just 2 units away. So I would imagine that the absolute value of 2i should be just 2. And I'm going to double check it with the formula so you can see. I would get absolute value of 2i is equal to the square root of 0 squared for the real part, because there is no real part, plus b squared, which I'll just put the 2 again, leaving off the I part, because I don't need that when I'm doing absolute value, because it's a real number. It's a distance. That gives me the square root of 4, which is 2. So that does make sense. My absolute value should be 2. Now let's look at this last example, 3 minus 6i. So here I'll go to that real part 3. And the imaginary part, negative 6i, and plot that point. You'll see here I'm writing down what a and b are, just so you can know when I'm plugging into that absolute value formula later. So I'll go to 3, then negative 6i. And again, I'm going to find that distance from the origin by using that formula written up top. So the absolute value of 3 minus 6i, or its modulus, would be the square root of a squared, which in this case would just be 3 squared, plus b squared, which is negative 6. So this would be the square root of 9 plus 36, which would be the square root of 45. And there is a perfect square in there, which is 9 times 5. So 3 square roots of 5 would be the absolute value of 3 minus 6i. And that is how you simplify, graph, and find the modulus of complex numbers.